Hi, this is our presentation for the Refrigeration Lab between my group, consisting of me, Mayur Singh, Christian Kandi, and Emily Lin. The goal of this lab is to cool an aluminum block using the above refrigeration system to determine the efficacy of a third-party vortex tube. Modeling of the entire system is required to obtain sufficient reference points of performance. Our refrigeration system has 5 points of interest to model. We have our vortex tube, boxed in red, our aluminum block, our regulator compressor, our heat exchanger, and our accumulator. At these 5 stations, we can model and measure the temperature entering the vortex tube, the flow rate entering the vortex tube, the temperature and pressure exiting those tubes from a hot and cold exit, and as well as our heat exchanger. During the second week of testing, every component past the vortex tube is functionally identical, but we add a compressor driven by an electric motor. The heat exchanger cools air back to ambient temperature, and the accumulator stores the air to smooth the pulsing from the compressor output. During the first week of testing, our goal is to characterize the steady state behavior of all the components at various line pressures. This includes our vortex tube, our motor, our compressor, our heat exchanger, and our accumulator. We will also determine the experimental resistance of the styrofoam, our insulation.
In order to properly characterize the behavior of the vortex tube, we need to analyze the temperatures, pressures, and flow rates at steady state for various nominal pressure conditions. We use the shop air supply for easy control over input pressure. This graph shows the temperatures in the system as a function of time. You can see that the system has reached steady state in the green highlighted sections. The hot and cold outputs of the vortex tube reach steady state quickly, so these values can be trusted. The temperatures of the load and the system output, however, might not actually be a steady state in our analysis, so we should be aware of this when considering sources of error. Similar to the vortex tube output temperatures, the pressure at station 3, as well as both hot and cold air mass flow rates, reach steady state quickly after each pressure change, and can therefore be trusted. Plotting the hot and cold output temperatures of the vortex tube against the pressure at the input of the tube shows the following trends. The cold temperature decreases parabolically as pressure increases, and the hot temperature increases linearly as pressure increases. When looking at the mass flow rates as a function of pressure, we see that the cold air flow rate increases linearly as pressure increases. We also see that the hot air flow rate increases in a concave down parabolic fashion. When considering all of these relationships, we can see that the general trend is that when we increase the pressure at the input of the vortex tube, we will decrease the temperature and increase the flow rate of the air that's going to be applied to the load.
At 0 psi, or when the system is not operating, the compressor, vortex tube, and aluminum block temperatures are highly stable and trustworthy. The closeness of data for the compressor, aluminum block, and vortex tube makes sense because no cooling has occurred. The lower temperature from the exit of the aluminum block is due to conduction heat transfer from block to air. Below is data for the compressor and vortex tube at 20 psi. The temperature exiting the compressor takes a long time to approach a steady state value, which indicates that the compressor appears to be 312.6 Kelvin, but this reading does not appear to be relatively stable for the entire 18-minute run. Pressure exiting the vortex tube takes a moderately long time to reach steady state, at around 11 minutes, to stabilize at 247 kilopascals, providing some confidence to that value. At 40 psi, the vortex tube pressure does not approach a reasonable steady state value for the sampled time. Data appears to be incredibly noisy as well. The temperature reading has the same issue and only appears to stabilize at the end at approximately 340 K for the compressor temperature. The pressure reading seems to approach 391 kPa. Below is a model of our motor RPM versus our vortex tube pressure P3. We suggest that we have a relatively linear relationship between our RPM and pressure, though with the only 3 data points between 0 and 40 psi taken at 0, 20, and 40 respectively, our fit doesn't appear to be great, More data points could probably refine the quality of our fit.
In the compressor system, we need a heat exchanger and accumulator to cool the air to ambient temperature and smooth the input flow of the air. To quantify this change, we calculate the enthalpy change across both devices, seen in this graph as a function of pressure. We can see that as the pressure increases, the heat exchanger and accumulator will remove a greater amount of energy from the system. The temperature at station 3 has been significantly cooled from the temperature at the output of the compressor, and is close to ambient temperature, so we can conclude that the heat exchanger is working well. However, from previous graphs, it's clear that the pressure at station 3 is still pulsing slightly, so the accumulator could use some improvement. In order to quantify the ambient heating of the load at steady state, we must first calculate the thermal resistance of the insulation. This can be done both theoretically and experimentally. Theoretically, we can use the definition of thermal resistance and the dimensions and properties of the insulation to derive a value. Experimentally, we can rearrange the load's energy balance at steady state to calculate the resistance with experimentally collected data. As you can see, the theoretical value is about an order of magnitude greater than the experimental values. This could be due to the fact that an entire face of the load is exposed to the air without insulation, causing the load to lose heat quicker.
The goal of week 2 is characterizing the transient heat transfer at the aluminum block, which will help reveal the load's material properties. These experimental results will then be compared to the accepted values, and afterwards, the uncertainty and EPA analysis will be performed for the steady state energy, the thermal resistance, and the total transient energy uncertainty. A lump capacitance model will be used to determine the load's energy rate of change, which is represented by the first equation. The expression will then be integrated to find the total energy change, after which we will need to calculate the Q error to represent the discrepancies in the system. If the W error is all in the load temperature energy, then it will be necessary to experimentally identify the load's specific heat capacity, which is then used to determine the Q error. Uncertainty analysis will then be performed after the initial calculations. The uncertainties for the hardware used is tabulated in the first figure. Using these values, it will be possible to find the steady-state energy uncertainty by calculating the Q.air and Q.ambient, both of which have equations that require further EPA analysis. These equations are annotated based on given and measured parameters and those with negligible uncertainties. The combined uncertainty for insulation resistance can also be calculated using the equations listed. The final uncertainty value for the mass flow rate, Q.air, Q.ambient, and insulation resistance are detailed in the table. The mass flow rate for the cold stream and Q.air uncertainty seem to increase as pressure increases, since increasing the pressure increases the final velocity per the Bernoulli's equation, and therefore the mass flow rate will also increase. A larger uncertainty will be expected with the larger value. The total transient energy uncertainty can also be calculated by performing EPA on the delta Q air equation and delta Q ambient equation. The uncertainties for each respective heat transfer equation are summed, since they are integrated over several time steps. Finally, the load heat transfer uncertainty can be determined by performing EPA on the Q load equation. Afterwards, comparing the Q air equation and Q total equation will yield the capability to calculate the Q total uncertainty. Here were some of the references we used, and that concludes our presentation for today. Thank you for your attention.